When I have a positive velocity, that's going to mean that you are moving, depending on the context of the problem, you could be moving up, forward, or right. So any type of like positive movement is going to be associated with a positive velocity. A negative velocity was going to be that you are moving down, backwards, or to the left. So we have a positive velocity, and then we also have a negative velocity. And then we also have a zero velocity, which what do you think a zero velocity is going to mean? Not moving. But I am going to make that a little bit more clear. So it can mean not moving, even if for a moment. And I include that even for a moment there because if you think about it, if something is moving and it changes direction, there's like that brief pause where it appears to kind of just like freeze. Like you think about like a ball and you throw it in the air, that's like that brief moment at the very top where there's like that hang time as it's like changing direction, starts falling back down. Or like if I'm walking forwards and then I change direction, start walking backwards, there's like that split instance where like my velocity is zero. So when we see a velocity of zero, don't think that like we're sitting down completely and resting. It just means that like for a brief instantaneous moment, movement has stopped. The notation that we are going to be using for velocity, really only one that we'll use like f of t, v of t for velocity, wherever that came from. Another notation we can use is going to come from like the definition of what I call absolute, not absolute, average velocity and instantaneous velocity. I often see students mix up these two definitions. So we have the average velocity and the instantaneous velocity. The average velocity in calculus, when you see that word average, that's typically going to be like an old school slope formula. So like the change in y over the change in x. Whenever we see average velocity, it's going to be like a before calculus type problem, which still shows up. If I say find the average velocity from t is equal to p to t is equal to q, average velocity again is literally the change in position. I'm going to use y for position. The change in position over the change in time, using delta there to represent like old school slope. Or you can think of it as, so I have y of p minus y of t over y of p minus y of q, over p minus q. So average velocity is an old school slope formula. I'll make that look a little bit nicer. To connect to some things that we have already talked about a little bit in this class, when I say average velocity, that's actually the slope of a secant line, since it's the slope between 2 points on the graph. And it's going to be the slope of the position graph. And some of you might remember if you have taken physics, again, I'm going to treat it like we haven't taken physics, but if you were asked to find the velocity from a position graph, you just do like the change in the y over the change in the x. Where the calculus comes into play, we often don't want to find the average velocity. Like if I would put this in terms of like you driving to school, like there's definitely like some speed that you like average. Like sometimes you're going fast, sometimes you're going slow, sometimes you might be going too fast, but you have like some average velocity over the whole trip. Instantaneous is like how fast are you going at a particular moment in time. This is where the calculus comes into play. The instantaneous velocity is still the rate of change of the change in position over the change in time. But it's going to be at that instant. So this is going to be actually a derivative. And velocity, big idea for today, is literally, so I have the change in position over the change in time. I'm going to write it as dy dt, which reminds us that velocity is literally the derivative of position. So it is going to be the slope of a tangent line versus a secant line, but still the slope of the tangent line position graph. So if you're looking at this handout, You can kind of see where we're headed with this. If I have position, I have it written kind of along the side. You have position, you take the derivative of position, and it's going to give you velocity. So we can think of position as literally the derivative of velocity. And then from velocity, we also are going to have the acceleration. The acceleration we're going to define as the rate of change of velocity. With respect to time, not over time. You can see along the side, I have like, if we have position, you take the derivative that gives us velocity. Well, the derivative of velocity is going to give us acceleration. The main notation we're going to be using for acceleration is a of t, but a of t is literally going to be the derivative of velocity, which if acceleration is the derivative of velocity, what derivative is it of position? The double prime, the second derivative. And so when we're analyzing these functions, we're going to see a lot of stuff similar to that chart we did way back in Unit 2. Like we'll be able to think of acceleration as the second derivative. We'll be able to interpret velocity as the first derivative. And we'll be able to interpret position as the original function. Do need to know what it means to have a positive velocity, positive acceleration, negative acceleration, or a zero acceleration. For us, we're going to define a positive acceleration. That means velocity is increasing. A negative acceleration is going to mean velocity is decreasing. I would advise you against using the word like decelerate. Like you may like decelerate in a car, but when we're talking about calculus verbiage, we're going to say like positive acceleration just means velocity is increasing. A negative acceleration means velocity is decreasing. So when I say a zero acceleration, I'm going to put that into like calculus content. And so when I say a zero acceleration, that means that the velocity graph has a horizontal tangent line. And so similar to velocity, we have the average acceleration and the instantaneous acceleration. Average acceleration is going to be like an old school slope formula, change in y over the change in x. Instantaneous acceleration is going to be where the derivative comes into play. If we're doing the average acceleration, we know acceleration is the change in velocity over time. So we can think of the average acceleration as the velocity at q minus the velocity at p over q minus p. Average velocity is going to be the slope of a secant line on the velocity graph. Comparing that to the instantaneous acceleration, the instantaneous acceleration is the slope of a tangent line on the velocity graph. And then we already kind of wrote it out to the side, but we can define acceleration as the derivative of velocity or the second derivative of position. And that's like the first kind of big idea that we'll see a lot in this class, especially whenever we're discussing position and velocity acceleration, is how they're related to each other in terms of calculus. For those of you who have taken physics, are currently in physics, like if you go and look at some of your kinematic equations, like they might give you one for like particle motion velocity. Like literally, if you look at that one, its derivative will be like the acceleration equation. Like that's the connections we have between these graphs. Before I talk about speed, any questions or things I can clarify from the first three rows on that chart? All right, and so then the last word I want to do is speed. Speed is something that I see students mess up on because they're like, well, we just talked about velocity. Is speed really something different? And for us, yes, we are going to define speed as something different. For us, the definition of speed is it's called the magnitude of velocity. basically it's going to be the velocity, but you removed the direction component from it. So we can define speed as the absolute value of velocity. So if I say my velocity is -8, the speed would just be +8. If I say my velocity is +8, well, the speed is still going to be +8. And so often one common question that we're going to be asked is to determine whether something has an increasing speed or a decreasing speed. The biggest mistake I see students make is when they talk about something decreasing, they just want to look at like, oh, well, the acceleration will tell me whether the speed is increasing or decreasing. The tricky part with this is we have to consider like the direction something is moving in. So I'm going to let you write it down first, and I'll kind of explain it. We're going to say that the speed is increasing when v of t and a of t have the same sign. The speed is going to be decreasing when v of t and a of t have opposite signs. And there's different ways that that can kind of show up. So speed is going to be increasing if maybe say like the velocity is positive and the acceleration is positive. Speed would also be increasing if velocity is negative and the acceleration is also negative. Some equivalent ways I can write that statement. So since we know that velocity is, its derivative is acceleration, this first statement I wrote down where velocity is greater than 0 and acceleration is greater than 0, an equivalent way of saying that statement is v of t is positive and increasing. Where that's coming from, we know that acceleration is the derivative of velocity. So if velocity is increasing, that means that its derivative is positive or acceleration is positive. Velocity is also equivalent statement is if it's negative and decreasing. Most students have trouble thinking about that second case because they're like, well, if acceleration is negative, like how does that mean that the particle is speeding up? And the way I think about it, in velocity, the sign of it just tells you which way you're going. So if I say a negative velocity, that just means like I'm moving backwards. And if my acceleration is also negative, I'm going to be like pushed further backwards even faster. So it's kind of like the acceleration and velocity are working together. So then likewise, speed will be decreasing when they have opposite signs. So you can think of it as either v of t is greater than 0 and a of t is less than 0, or v of t is less than 0 and a of t is greater than 0. I think about speed is going to be decreasing when the velocity and acceleration are working against each other. So like one is positive while the other one is negative. Another way to translate this first statement would be something like velocity is positive but decreasing. So you're moving to the right, but that velocity is slowly slowing down. Or velocity is negative, so maybe something is moving backwards, but that velocity is increasing, so it's still going to be slowing down while still moving backwards. I think a lot of these topics, you just kind of like do examples and like certain things that start like clicking. I don't have a lot of examples for notes, so like on the second page or on the back if you're in person, we're just going to talk about like what these graphs look like. And then I often find students have the most trouble interpreting the graphs of these. Tomorrow we'll kind of regroup and I have an algebraic example to do as well. Before we look at those examples, does anyone have any questions on that front page? All right, let's go ahead and flip it to the back and we'll see where that puts us. So I want to start off by filling in this table. I'm going to explain what it means. So I've made it, and I don't know if it makes sense the way I kind of designed it. But one thing I often in the past found students have issues with is understanding like Like you can say, oh, the derivative of position is velocity, the derivative of velocity is acceleration, but really understanding how those interact with each other, I sometimes find just some like misconceptions. So I made this, and I don't know if it helps or doesn't, because I kind of rewrote my notes from last year, but we'll see how it goes. So what I have is I have a description that basically has two qualities on it. Like in that first one, I say we have this generic thing, we'll call it like a particle. And I have that it is moving forward with a constant velocity. So I want us to interpret what that means, like what does that mean about the position equation? What does that mean about the velocity equation? What does that mean about the acceleration equation? And then just draw an example of what that graph would look like. So let's look at the first part of what it says. I have that this particle is moving forward. Well, if something is moving forward, is that giving you information about the position, the velocity, or the acceleration? Position. And that's what you want to be careful with. So which one is actually talking about movement? Velocity. So when you say position, that just says like, I am here. Like I'm standing somewhere, that's my position. We don't know anything else about that. Velocity is what's going to talk about movement. So if I say something is moving forward, what do we know about that velocity? Is it positive or negative? Positive. Positive. So forward movement is going to be positive. So I know that velocity is positive. And then the second statement is a constant velocity. Well, if it's constant, then that just means that my velocity is, I don't know, it's just constant. That's what I need to know. So when I'm going to start drawing out these graphs, we're going to interpret position as the original function, velocity as the derivative, and acceleration as the second derivative. So let's think about what that means. If I say velocity is positive, that's the same thing as saying the first derivative is positive. If the first derivative is positive, what do I know about the original function? It's increasing. So if I say velocity is positive, that means the original function, which is position, would also be increasing. Other thing we know, if I say my derivative is constant, we know that the derivative is just a fancy way of saying slope. So if I say that my slope is constant, what do I know about the original function? What type of function is it? Linear. So if my velocity is constant, then my position is going to be linear. Do we know really anything about the acceleration? Technically we do. What's the derivative of a constant? Zero. So if my velocity is a constant, its derivative acceleration would be 0. So I can just draw like some sample graphs of this. Again, there's not just one answer for this. So my position needs to be increasing and linear. So bam, increasing and linear. I don't know the specific y values, but I know it should be increasing and linear. My velocity needs to be positive and constant. So positive and constant. And then my acceleration is 0. So those are going to be my position, velocity, acceleration graphs based off of what I see. Let's look at number 2, and then I'll let you try 3 and 4 on your own. First statement says we have this particle and it's moving backwards. What is that telling us, and which function is that telling us something about? Velocity. Moving backwards would mean negative. And then we have decreasing velocity. Well, when I give you a decreasing velocity, what is that really giving you information about? Acceleration is negative. So let's think about it this way. So decreasing velocity. So that is kind of clearly telling me that my velocity is decreasing. So think about this in terms of the chart that you have. When your first derivative was decreasing, what did that mean the second derivative was? Negative. If my acceleration is negative, that's the same thing as thinking about the second derivative. What did a second derivative being negative mean about the original function? Concave down. Concave down. So I know that my position equation would be concave down. And then if my velocity is also negative, I know my original position would be decreasing, because velocity is just like the first derivative. A negative first derivative means my function is decreasing. So drawing in just a sample, again, there's more than one right answer. I need a position equation that's decreasing and concave down. There we go. My velocity needs to be negative and decreasing, so it's going to be below the x-axis and decreasing. And my acceleration is going to be negative. Again, there's more than one right answer for those. I'm just kind of giving us a general idea of the comparison. Yes, both.
By decreasing velocity means getting it's going backwards quicker.
So when I just say decreasing velocity, all that tells us is like whatever some initial velocity is, the values are getting smaller. So like if my initial velocity is say like 5, my velocity would be going from like 5 to 4, 3, 1. But it could also mean, like say I was already moving backwards at like -2, then it would be like -2, -3, -4, -5. So really we just have to interpret as like in calculus that a decreasing velocity just means that the acceleration is negative. And that's also coming from, if you just think about it backwards, what we wrote down on this first page. There it is. A negative acceleration means the velocity is decreasing. And that's how we're going to define acceleration. Go ahead and try those second two for me. And then we will go over them and we'll start some of the problems underneath it, but we probably won't get a chance to finish them. I don't want to rush them. So try 3 and 4. Number 3, I want you to see if you can figure out relationships between PVA. When I say that this is moving downward with a decreasing speed, you might need to go back and flip over or switch over to remind you what a decreasing speed would need to look like or what that means. And then number 4, we're moving to the right with a positive acceleration. So in that first row we see in number 3, it tells me that my particle or whatever it is moving downward with a decreasing speed. Let's do the easiest part first. Moving downward means that the velocity would be negative. If your velocity is negative, what would your position be doing? Decreasing. Again, velocity is the derivative, first derivative of position. And then when it comes to speed, this is a decreasing speed. Remember, we define speed a little bit differently in a math class. A decreasing speed, I wrote it out to the side, means that the velocity and the acceleration have opposite signs. So if this particle is decreasing, we already know that the velocity is negative. What would the acceleration need to be? Positive. If the acceleration is also negative, then it technically would be speeding up. The second derivative is really just acceleration. So a positive acceleration means your position will be concave up. Thinking about back to that chart from unit 2, if your function is concave up, that means the first derivative would be increasing, which would mean that the velocity would also be increasing. So like a sample graph we could use, my position would be decreasing and concave up. My velocity is negative and increasing. And then my acceleration is just positive. Questions on number 3? Is concave up, because we have to think acceleration is like the second derivative. So if my second derivative is positive, that means the original function, thus position, will be concave up. And then that fourth one, moving to the right, we know that that means velocity is positive. If velocity is positive, that's talking about really the first derivative is positive, so the original function would be increasing, the original function being position. And then a positive acceleration, If acceleration is positive, that means the original function is concave up, and the velocity would be increasing. So this graph we have is increasing and concave up. Velocity is positive and increasing, and the acceleration is.
So the first one be the, yeah.
Which one? I'm sorry.
The graph for position.
Position graph or
Increasing.
increasing. I got it. I see it. Thanks. Increasing and concave up. Thank you. Looks like that. Thank you. And then just for understanding, in the situation described in number 4, where I say it's moving right with a positive acceleration, would you say that this would be speeding up or speeding down? Speeding up. So again, velocity and acceleration have the same signs. So this problem is technically, whatever it is, speeding up. So in this class, there's really 2 ways we will interpret position and velocity and acceleration. We can do it algebraically, like we just learned a whole bunch of derivative rules. So like if I say, hey, position is 2x plus sine of x, find the acceleration, you just find the second derivative. We sometimes have these problems. We'll do things like sign charts, we'll do candidates tests, we'll do set things equal to 0, like all that stuff we've been doing with intervals of increasing and decreasing and concavity and extrema can show up with PVA. We just pretty much are giving it a different name. Instead of saying concavity, we're saying acceleration. Instead of saying increasing and decreasing, we're talking about the velocity. The example I want to start on today, and again, we might not do all of this because I don't want to rush it. I find most students have issues with the graphical examples. So that's what I wanted to use class time for. So I have a bug, just made it up. A bug is crawling along the y-axis because why would a bug not want to crawl along the y-axis? And so this bug is along the y-axis, and then this is a graph of the velocity. So we're not looking at the position, we're looking at the velocity graph. So we're kind of like looking at f prime. Not to scare you, but a lot of these examples are going to be very similar to like, hey, here's f prime, try to draw f of x. Or here's f of x, try to draw f prime. And we want to answer some of these follow-up questions. We're just going to kind of see how many we can get through. I'll stop at 3:20, and tomorrow notes will be a lot shorter. So look at number 5. I have what is the average acceleration between 0 and 6. When we see average in a calculus class, average is always going to be your clue that you're doing like an old school slope. Change in y over the change in x. If I'm doing average acceleration, you know that average acceleration is literally just the change in velocity over the change in time. This is actually from an actual AP exam. They asked you to show your work just so you can verify that they know where these numbers are coming from. So I have average acceleration. What do we know average acceleration is? Is the change in y over the change in x, the change in velocity. So I'm going to have like v of 6 minus v of 0 all over 6 minus 0. And then we can just read our graph to answer the rest of the question. What is the velocity at 6? The velocity at 6 is 1. What's the velocity at 0? 3. 6 minus 0, we're just finding slope. You can leave your answer like that. No need to simplify in my class. But it does simplify to negative 1/3. No units were provided, so we don't need to really worry about the units for these problems. Sometimes we do have to justify your answers, so like that one we really didn't have to justify, it just asked us to show our work. Let's talk about 6. It says, when, if ever, is the bug at rest? Now you know when I like doing these problems, I sometimes do my justification first to help me form my answers. If I'm looking for when the bug is at rest, what does that mean in like calculus terms? But we're looking at the derivative. We're looking at velocity already. So what would velocity be if you're at rest? 0. So like my justification would be because v of t is equal to 0. Sarah, you're correct if you were looking at the position graph. That's where the horizontal tangents would be. So looking at this one, where is the velocity equal to 0? 3 and 8. Again, that does not mean that the bug is actually stopping and chilling. Like that just means that like at that split moment, the bug has a velocity of 0. So a little bit different of what we picture like at rest. So that would be the answer for that one. Let's look at 7. When, if ever, does the bug change direction? So again, I like doing my justifications first. If we're talking about changing directions, are we going to be most concerned about the position, the velocity, or the acceleration? What tells us about the direction we're moving in? Again, not position. This just tells you where you're at. Velocity. So which one's actually talking about movement would be the velocity. So if I'm going to say it's changing direction, what's really are we talking about is changing? The what with velocity? Someone said it. The sign of velocity. So when, if ever, does the bug change direction? Again, if I want to do the justification first, it will be because v of t changes sign. If this was an algebraic problem, this would be one where we would make a sign chart, but we can just kind of look at this. When, if ever, do we see a t-value where the sign of the velocity changes? 8. And it's just 8. So do be careful. Like, it does, the common other answer people put on here, the wrong one, if t is equal to 3. But if you're looking at 3, we have like positive velocity, still positive velocity. So it doesn't change at 3. But at 8, we see we have positive velocity, then negative velocity. So it's changing direction when t is equal to 8. Let's look at number 8, and this is where I'm going to stop today's notes. So looking at number 8 says, when, if ever, is the bug's acceleration positive? We are looking at the velocity graph. So what does it mean in terms of velocity if the acceleration is positive? Increasing. So we're going to say my reason acceleration is positive because v of t is increasing. On what interval do we see an increasing velocity? 3 to 6. And for these, we always use parentheses. Don't worry about brackets when you're doing your intervals. So I'm going to stop there. Like, I don't want to rush 9, 10, and 11, and we'll kind of pick up there. I am going to ask you to go ahead and start the homework, though. So tomorrow, what we're going to do is we're going to finish those 3, and then we're also going to look at an example of PVA algebraically. I just have 3 problems. Your homework that you're working on is in OneNote. I am only asking you to do, I already forgot. It's either the odds or the evens, but I highlight the questions so it will be clear. You're basically doing every other one. It's called a packet, but it's really not that long. So you're only doing half of the ones from homework 6. Homework 7 I did take out, and it will be optional, so like let me know if you want more PVA problems to practice, and I can give you an additional homework. Looking ahead this week, we have just homework 6 and then homework 8. Next week will be just us working on the briefcase binder and reviewing. Please also don't forget that your take-home test is not due Tuesday, unless you just want it to be, but it is due Wednesday at the start of class. Little bit of time left, but I think that will give you a chance to go ahead and get started on the homework. Just make sure that like some of this is like clicked before you're on your own and at home. Tomorrow we'll regroup, answer any questions you have, and I'll finish these notes on PVA. But this is one of the topics that like, I know I say this a lot, but it's one that just like never goes away. Like second semester when we're doing integral calculus, like it's going to show up again, and then it kind of just keeps on showing up. So you either get PVA now, or you'll be forced to get it later, or you just fail. I don't know. Yeah. But y'all can go ahead and get started on that. Let me know if you have any questions. Anything else I need to tell you? No. Y'all can go get started. Those of you who are at home, we will regroup and just start again tomorrow.